In this video, we're going to talk about tuning wire antennas. We're also going to talk about my favorite tool for doing that. So you take this thing out of the box and you charge it up and you turn it on. And the first thing you're going to have to do is calibrate it. And to do that, they typically will give you 3 calibration pills that you use. And one of them is going to be an open circuit. No, that's not it. This is the open circuit. And then this is a dead short. And then this is a 50 ohm load. And you don't want to just do it right on the port of the device, because in order to get to whatever our antenna is going to use for coax, we're going to have some sort of an adapter, an SO239 or what have you, and it's going to be on the end of a short piece of coax. And we're not measuring this. What we want to measure is just the antenna. So where we start measuring, we want to calibrate from here. And even then, we're going to be measuring our coax along with the antenna. But that's better than measuring a piece of coax that's not going to be attached to your radio. So at least, if we measure from this point, what we're measuring is what the radio is going to see, which for the most part is the most important thing. After all, it's the radio that wants a low standing wave or low SWR. So in order to do that, we need some sort of an adapter. In this case, it's just an SO239 to SMA. And we'll screw that on. We'll start with our open. And then we have to pick our frequency range. If you're putting up a brand new antenna that may be way out of frequency, you'll want to go wider or broader than what you think you may need. In this case, all these antennas I've already checked. I know where they are. This is 3.5 to 55 megahertz. So the way you do this is you just select and type in your frequency. So 3.5, and then up here 55 meg. And now that's our frequency range. You'll be more accurate if you just calibrate through your frequency range. And remember, it only checks a certain number of points across the screen. So if you can narrow your range up, the resolution is going to be better. So I've got the open pill already on here, and I'm going to touch the screen. I'm going to hit calibrate. I'm going to calibrate the open. I'm going to take that open pill off. I'm going to put the shorted pill on. And then we'll go to our load. The load is a silver color instead of copper or brass colored load. And then if we were using the other port 2 on this device, then we would continue with isolation and through, but in this case I'm not doing that. We're only working off port 1, the single port. So I'm just going to hit done and save. So that's calibrated. We'll move these pills out of the way. We'll take our adapter off. And we'll screw our antenna on. Now, there's a lot going on here, isn't there? I recommend that the first thing you do is get rid of all of your traces except for SWR. And in order to do that, we're going to go back to the display screen. We're going to hit trace. And then the SWR trace is up here in the left hand corner. You can see it's yellow. So we're going to leave it, but all the other traces we're going to get rid of. And the way that you do that, you just click on it once to select it and then click on it again to remove it. So the green one we'll get rid of, the purple one we'll get rid of. Now we're down to a single trace. It's still too much to process. So what you can do at that point is just narrow down on the particular frequency range that you want to check. And in this case, on this antenna, I put this antenna mostly for 20 and 40 meters. So I'm going to go ahead and I'm going to change this to reflect that. Now it's starting to be a little bit sane, and we can see what's going on. We see three distinct resonances of low SWR. This bottom resonance is going to be 40 meters or 7 megahertz. This upper resonance is going to be 14 megahertz. And in the middle we have another one which is somewhere around 10 or 11, but I don't care about that one because I'm never going to use the antenna there. There's a little knob up the top here that you can use to manipulate the markers and some of the settings on the nanoVNA by moving it. And you can see in this case what it's doing is it's moving the stop point and changing it. So the stop point is over here, so if I go up you can see it becomes 17 megahertz and I go back down to 15. And the way that we can stop that from happening, there we go. That's how you do it. So search minimum and it'll find the minimum wherever that may be to get the trace back or get the marker back. Okay, now that the marker's back, if you grab this marker and move it now, when you move your button on the nanoVNA, you're actually moving the marker. So let's go all the way to the bottom first. There's our low point at 40 meters, 7 megahertz. Now we can see it's actually pretty good. It's 1.09, 1.1 at 7.2, and if we go down in frequency, the SWR starts to go up. If we go up in frequency, it starts to go up. And then we'll check out this middle resonance, which happens to be at 11 megahertz on the nose, and it's 1.05 to 1, 1.06. And we'll go to the 20 megahertz resonance, which is 14.680. So this is my multi-band wire dipole that I just put in the air. It's an off-center fed dipole. That's the reason we have two distinct resonances. But if I change antennas, let me change to my other fan dipole. And this antenna is a fan dipole with 40 meter and 80 meter elements. So once again I'm going to search minimum. And you can see that at 80 meters, 3.860 megahertz, we have a 1.1 standing wave, and typical of 80 meters, the bandwidth is pretty narrow. And then we can come up to 40. And at 7.190, it's 1.37 to 1. So this 40 meter fan dipole, the 40 meter section of this fan dipole has never had a really, really low SWR, but it's a very good performing antenna. SWR isn't everything. Okay, so let's go back to, well, let's check our 10 meter beam while we're here. Okay, now we're on a 10 meter Yagi, which has this weird resonance at 7.190, but we're going to ignore that because it's a 28 megahertz antenna. And there we go. So you can see that this one, its best SWR is at 28,130. It's actually a little bit low on frequency. And we can come up and get into the center of the band, and you can see it's still okay. But this antenna is due for a remake anyway, so I've never messed with it. At some point I'm going to take it down and add 20 meter elements to this antenna. But that's the 10 meter Yagi. And our off-center fed dipole has a resonance on 10 meters. So you can see, let me broaden this up a little bit, that it's actually usable on the 10 meter band. Right there's the calling frequency, it's 1.9, my radio will tune to that. So, like most off-center fed dipoles, it's multiple resonances. Okay, so that's measuring SWR. But there are more useful measurements that we can do. So what I've done is I've narrowed in on the 40 meter portion of this antenna. And you can see that the SWR is very good. It's 1.02 to 1 at 7.255 megahertz. That's outstanding. And as we go up, you can see the SWR starts to climb, 1.3, 1.4, 1.5. So let's say that our radio demands an SWR that's 1.5 or less. So the upper part of our bandwidth would be 7.33 megahertz, and a lower part, 1.3, 1.4, 1.5, would be somewhere around 7.190. So that would be the bandwidth of this antenna if we had a radio that demanded 1.5 or 1 to less all across the usable part of the band. So that's how you can check bandwidth on the antenna, is just check the bottom and the top of the SWR requirements of your particular setup. Now if you have a tune-year radio, obviously you can go a lot further. We can go all the way up to 3 to 1, and in some cases higher than that. So there's 7.045 and 7.465. But this antenna, it actually came out very good as far as 40 meter goes, but 20 meter wasn't quite so lucky. So here's 20 meters, and you can see it's a little high on frequency, 14,670. We're at 1.12 to 1 roughly. And to get down, oops, I forgot to set my marker. Okay. To get down in the usable portion of the band, it's going to be out of band somewhere right around here. So from this point, 14,350 and down in my case, it's already 2.1 and it goes up. But once again, the radio will tune to that. But if you're using a radio that does not have an internal tuner, then this antenna wouldn't work for you because of that. And this is a result of end effect. But okay, so that's SWR, the single SWR trace. Not very confusing if you just get rid of everything else and just look at SWR. But when you're tuning, you really want to look at other data that this device is capable of giving you. And in particular, what you want to look at is the Smith trace. So we're going to go back, display trace, and I'm going to select trace 1, and it's selected and it's turned on now. Now I'm going to change the format. I'm going to put Smith. And the reason that this trace is valuable is because what it gives you is the actual impedance of the antenna. In this case, we can see at its lowest SWR point, it's 49.8 ohms, which is what we would expect. After all, if everything is good, this antenna should be pretty close to 50 ohms. That's what the transmitter wants. Now we're back in the middle. 7.252 is where this antenna is resonant, 1.02 to 1. And let's bring up another trace. So I'm going to bring up the green trace, and I'm going to format that as reactance. Now we have a reactance trace over here. Now the thing about the reactance trace is it's measuring the reactive component in this antenna and the coax. And as we change the frequency, you can see over here it's going negative. So a negative reactance number is actually capacitive reactance. And if we farther this way to higher frequencies, you can see it becomes positive. So the negative sign goes away, which tells us that's inductive reactance. So if it's a negative number, it's capacitive reactance. And if it's not a negative number, it's inductive reactance. And now, how does this apply to us when we're talking about tuning an antenna? Well, the thing is, when you're tuning an antenna, what you want to pay attention to is two things: the SWR and the impedance. And what I will do is I will take notes. So what I will do is I will mark down the SWR at a given frequency. I will mark down the Smith impedance number at that frequency, and then I will mark down the actual frequency. So in this case, on a piece of paper, I'm going to put 7.256 megahertz, and I'm going to put 1.02 to 1, and then I'm going to put 50 ohms on that piece of paper. And the reason that I do this is because as I make an adjustment, I want to see what happens after the adjustment is made. So let's go ahead and do that. I'm going to go outside and I'm just going to take 3 feet off of one leg of this antenna, and we'll come back and we'll measure it again. Okay, I folded back 4 feet of this antenna. What I'm trying to do is deliberately mess it up. So let's pretend that we just put this antenna up and this is the numbers that we got when we did that. And you can see that, by making this antenna shorter, of course it made it higher in frequency, but it did something else as well. It kind of messed up our SWR number. It was 1.02 before, now it's 1.1, which is still a great SWR, don't get me wrong, that would be perfectly acceptable. But we're also high in frequency, now it's 7.355 megahertz instead of 7.2 something megahertz. And you can see our impedance is no longer 49 point something ohms, it's 50.6-ish ohms. And we have a little bit more reactive component now at -5 capacitive reactance ohms. As we go higher in the frequency, we can see the numbers change. You can also see that our capacitive reactance kind of hangs in there past the lowest frequency point. But the point is, let's say you put this up in the air and this is the number that you get. So obviously you know that it's high in frequency and you're going to have to get it lower in frequency. So you know you have to make it longer. And this is where tuning multiple resonances becomes a problem with off-center feds or end feds, because you're not just tuning one frequency, you're tuning multiple frequencies. So you can see we also pushed the 20 meter portion of this antenna higher. In fact, I need to go all the way up to 16. So checking the 20 megahertz or 20 meter band, 14 megahertz, you can see that it's way high. It's 14.920 megahertz. So it's a good 700 kilohertz, 600 kilohertz above where we need to be. But the point here is that as you make adjustments, you're not just affecting one band on an off-center fed or an end-fed dipole. You're affecting all of them. And even worse, an adjustment you make to a lower frequency band is going to have a large effect on an upper frequency band. So if you take a foot off one element at 40 meters, that's going to drastically change 20 meters. So it's a balancing act on off-center feds and end feds. And sometimes you have to shoot for a compromise where, let's say, you're a little bit low on 40 meters so that you can get 20 meters or even 10 meters to work out for you. So that's the problem with off-center feds and end feds. By far, they're the hardest wire antennas to tune because there's so much going on. And one adjustment doesn't affect just one band. One adjustment will affect all of your bands. Not only just in center frequency, but also in impedance, which directly affects your SWR. So it's a balancing act. You have to trim each leg individually and try and get to a point where all of the bands will work favorably. Now on this one, I'm actually quite happy that 40 meters turned out the way that it did, and I can accept the little bit of mismatch at 20 meters because I don't spend a lot of time on 20 meters. So it's nice to be able to get on 40 meters without a tuner and chat with local nets and just chat with people, within a 700-mile radius of me. And then if I want to do some DX work on 20 meters, I can just turn the tuner on and tune to the frequency that I'm running on 20 meters and have at it. Anyway, back to tuning this antenna. Let's go ahead and write down these numbers. I'm going to write down, let's just do 40, because 40 we know we'll get to a very low frequency if we do this correctly. So I'm going to write these numbers down. The low point on 40 meters, just happens to be 7.355 megahertz. So I'm going to write 7.355, and then in parentheses I'm going to put 50.4 ohms. That's our Smith reading. And then I'm going to put 1.11 SWR. Like so. And now I'm going to go out and lengthen that leg again. Okay, I've lengthened it back to where it was before. And what I will do at that point is I will center it up on the band, find the lowest SWR point, and then I will mark down those measurements. So I'm going to write down 7.245. That's our resonant frequency, and then I'll mark down 49.5 ohms, and then the SWR is 1.025. Like so. Now the reason I do that is because when you're tuning the antenna, the impedance number is actually very, very useful. And the reason it's useful is because, especially when you're tuning end feds and off-center feds, you have to deal with multiple resonances. So when I first put this antenna up, you can see that I had 1, 2, 3, 4, 5, 6, 7 resonances on this antenna. And the first one started at 1.750 and it was 3.5 to 1 at 27 ohms. And then there was a resonance at 7.3 megahertz, 30 ohms, 3.6 to 1. And there was another resonance at 10.9 megahertz, 60 ohms, 2.4 to 1, and etc., and etc., and etc., and etc. So a couple things are evident here. Number one, 40 meters is slightly high on frequency, but more importantly, the SWR is way off. We're at 3.6 to 1. That's way high. We need to get that 3.6 to 1 number down. So when we're seeing 30 ohms on 40 meters and we're seeing 33 ohms on 20 meters, what that tells us is that the feed point is too high in the current pattern for both of those bands. And what we need to do is we need to change our feed point so that we lower the current pattern where the feed point taps into this dipole so that the impedance numbers go up. Remember, a high current means low impedance and a low current means high impedance. So as we change the feed point, we can push those numbers, those impedance numbers, up, which will push the SWR number down. Remember, this is going through a 4-to-1 impedance transformer, so 50 ohms is actually 200 ohms at the antenna. So the impedance numbers are very useful. And as you start adjusting those, you can drive an antenna and get it where you want it to be, and it's your best tool really. And the nanoVNA is probably the best tool out there for adjusting off-center feds and end-fed antennas because of that. So you can kind of see exactly what's going on. Off-center feds and end feds are by far the most difficult antennas to tune because of the multiple resonance. If you're doing a fan dipole, it's relatively easy because what you can do is you can tune your 80 meter portion. Let's say you're doing a 20-40-80, so a 6-element fan dipole. So you can put it up with just the 80 meter elements and tune those first and get those squared away. That's only one resonance on your nanoVNA. It's going to look something like this. And you make that adjustment and you get it exactly where you want it to be, and then you take it down and you add your 40 meter elements. So you add 2 wires for 40 meters and cut those to approximately 33 feet each leg, totaling about 66 or 67 feet, and you put it back up in the air. And the first thing you'll notice when you do that is now you have 2 resonances. You'll have a resonance at 80 meters, and you'll also have a resonance at 40 meters. And the 80 meter resonance will change a little bit. So it'll probably go lower in frequency, I believe. If I remember correctly, that's what happened to mine. So you'll tune your 40 and you'll tweak your 80 just a little bit to get it back. You might have to lengthen it slightly or shorten it slightly. You won't know until you actually do it. So then you'll have 80 and 40 figured out, and you take it back down and you add your 20 meter wires, so that's 2 wires of 16 or 17 feet each, totaling about 33 or 34 feet. And you'll put it back up in the air, and once you put it back up in the air, you'll tune your 20 meter elements, but you will probably have to tweak your 40 meter element and your 80 meter elements as well. So each consecutive band that you add to a fan dipole is going to cause you to go to the previous one and adjust it. And you always want to adjust your longest element, lowest frequency elements first, because you'll be taking several feet off of an 80 meter dipole to shift its frequency. And if you had your other elements up, let's say you had a 20 meter element up and you took several feet off your 80 meter dipole, that's going to significantly impact the tuning of the 20 meter dipole, because a 20 meter dipole you only want to pull about 3 to 6 inches off at a time. So get your 80 meter close, add the 40, get the 40 close, tweak your 80, add your 20, and then go back and tweak or tune your 20, and then go back and tweak your 80 and 40, and then you may have to tweak your 20 again, and then you'll have all 3 nailed down and you'll be done. But that's how you use a nanoVNA to adjust antennas. You can look at the 2 most important specs of your antenna, which would be SWR and impedance. And by using those 2, we'll get rid of that green trace because we no longer need it there. So these 2. So your Smith impedance number, which, you really don't even need to look at the Smith chart, although you can. If you want to learn how to do the Smith chart reading, you can find videos on YouTube that explain that very, very well. But I just look at the number. So 49 ohms, and it also gives you the capacitance or the inductance value. So you can see most of this antenna is capacitive. Very little of it is inductive, just a small portion. But that's basically how you do it. And it's just a juggling of lengths, and sometimes you have to change it and change the angle between the V, or maybe put it a little bit higher in the air, or move it away from something that is attached to ground. A lot of times when you're tuning an antenna, it can be off because of interaction with your tower or a metal garage roof or something along those lines. Trees, especially when it's raining, can affect the tuning of a dipole. But very valuable tool, very useful for tuning antennas, and grab one and try it out. You'll be picking it up very quickly, and especially if you can get rid of all the noise. When you first power one of these up and you see something like that can be kind of scary. That's intimidating. But with just a few short strokes, you can kind of zone in on what you really want to see, which is impedance and SWR. And that makes it a little bit easier to swallow, not such a bitter pill. There you have it. Thanks for watching.